And then we're just going to add some food coloring to make it easier to see.
The next step in our experiment is to take your 2 candles, place them in the center of the water, and light them with the butane lighter. For the final step, take your beaker or large glass and place it over top of the candles. After a little while of having our beaker over our candles, you'll notice the candle's flames will get smaller and smaller until they're extinguished. If you watch closely, you'll see that the water level underneath our beaker begins to rise as the candles fade away. The water level will continue to rise for a short time after the candle has been fully extinguished. You'll notice that the water underneath the beaker is much higher than the water in the shallow dish. In our experiment, our beaker is filled with gaseous air molecules. The energy from our flames transfers to the air molecules, exciting them by raising their temperature. When the air molecules in our beaker are excited, they try and spread further apart, but because our beaker won't expand like a balloon, the volume of space our air molecules can take up is limited. As they try and expand in volume, the air molecules press harder and harder against the walls of our beaker and the water at its base. This increase in air pressure under our beaker causes the water level under it to be pushed lower than the water level outside of it. The higher the temperature or the more energy the air molecules get, the more pressure will be created under our beaker. As the candle flames burn, they use some of the oxygen contained in the beaker for combustion. The products of this reaction are carbon dioxide gas and water vapor. As more and more hot carbon dioxide gases and water vapor are produced, they fill up the top of our beaker, forcing the oxygen in our beaker that the candles need to burn lower and lower until the candles are extinguished. Once the flame is extinguished, the air molecules under our beaker begin to cool off, dropping in temperature and losing their excitement. This causes the amount of pressure our air molecules are exerting on the sides of our beaker and the water at its base to drop. As the pressure drops, the air under our beaker wants to be equal to the pressure outside of our beaker. This need for balance causes a pull on the sides of the beaker and the water at its base. Because it's much easier to pull water into our beaker than it is to collapse the sides of our beaker, the water in our shallow container is pulled into our beaker, raising the water level under the beaker, equalizing its pressure. By changing the temperature under our beaker, we can clearly see the directly proportional relationship between the temperature and pressure of an ideal gas. This relationship is known as Gay-Lussac's law.